Unfortunately, I can't be with you live tonight. It's my little girl's 7th birthday, so I'm going to be celebrating with her. There we go. So this means that we won't be able to respond live to any of your comments, but hopefully this video will be useful to you anyway. It's triple only content for the physics exam tomorrow. There is not lots and lots of physics only content on the Spec 1 exam, on the paper 1 exam. The majority of this is focused in Spec 2 and Spec 4. I'm going to run through all of it. Hopefully it should take about half an hour. Okay, so we're just going to change the camera position and then we'll crack on. So the first thing that we're going to look at is the required practical, the only required practical that is a physics only required practical on paper 1, and it's the insulation, it's the effectiveness of different materials as thermal insulators. And I basically see this as one of 3 types of question. It's either going to be a method, or it's going to be to do with variables, or it's going to be something to do with a graph. And you can see an example of a question that we've got here. Here is the design of the experiment with the insulation, the metal can with hot water in it, and a thermometer. Obvious control variables would be the amount of hot water, the amount of insulation, the thickness of that insulation, the fact that it's got a lid on it there, the material that the metal can is made out of. And the dependent variable is going to be the thermometer, the temperature that we measure. The independent variable in this investigation is going to be this insulation. It's going to be the insulation that changes. Now often they'll give you a graph like they have done in this question here, and you have to interpret the differences between this graph. So things they might ask what is the room temperature? And you should be able to identify the room temperature there being 20 because that's the temperature where material C has stopped cooling. Should be able to identify the temperature of the water at the beginning, which you should be able to see there is 80 because they all start at 80 degrees. And then you should be able to interpret which of these materials is the best insulator. Material A would be the best insulator because the temperature decrease is the least between the beginning of the experiment and the end. Here we have an example of how they might bring variables into this question. If you look here, we have experiment 1 and experiment C, and there's a very, very clear difference between experiment 1 and experiment C, and that's the thickness of this insulating material here, which will have a massive bearing on the experiment. Therefore, this control variable is not well controlled and will have a big bearing on the experiment. If it is a methods question, make sure you talk about quantities. Make sure you talk about time, make sure you talk about control and things like that. Make sure you talk about the amount of water, how frequently you're going to measure the temperature, how accurately you're going to measure the temperature. Okay, that's actually everything from Spec 1 that's in the physics only content. Spec 2, the first thing that pops up that is just physics only is static charge. So it's linked to the electricity topic, but this isn't flow of electricity, this is static electricity. And what we have here is it's caused by friction. Okay, it's caused by the rubbing of 2 insulators together. And what happens when you rub an insulator, so we have fur and rubber here, when you rub those 2 materials together is you get transfer of electrons. So electrons move from one to the other, and you don't need to be able to say which way they go, you just need to be able to say that where they accumulate, that thing becomes negative. Whichever material the electrons move from, that becomes positive. So there's quite a good crossover there with chemistry and with your ions from your Spec 1 paper the other day. The other thing you need to know with static is how things respond when we have charged particles. So these two here, these 2 pairs, these are described as like charges. And where we have like charges, we get repulsion. Similar to a magnet, when we have north and north, we repel, south and south we repel. With charges, we get repulsion as well. And also similar to magnets, where we get opposite charges, like with opposite poles, we get attraction. The major difference though is this is temporary. So when this positive meets this negative, when they touch each other, that will lead to discharging. So the electrons that have built up here on this negative object, when these two touch or when they get close enough, they will jump to the positive object. This will become uncharged, and this will also become uncharged. The other thing in Spec 2 that we need to be aware of is electric fields. Now, you should already be aware that electric fields always go from positive to negative. And that's what you can see in this diagram here. We've got the positive charge and the electric fields are moving away from it. And we've got the negative charge and the electric fields are moving towards it. Just like with magnetic field lines again, the closer the lines, the stronger the field. So you should be able to see here that the closer to this object, the closer these lines are together, therefore the stronger that field will be. Same here, we have a stronger field close to the object, and as we get further away, the field lines get weaker. If I was asked to draw another one, similar to this one, where I was asked to draw a similar field, but a stronger field, the way that I would do that is I would add in more lines, and that would give me a much stronger field. Okay, they would move in the same direction still, but there would be a much higher density of electric field lines, and therefore that would indicate a much stronger field. Just like with magnetic fields as well, we can join these fields up. So if we have a positive and a negative, we might have these field lines starting to join to each other. And that's an attempt there, or a start to try and discuss sparking and basically electric shocks. And that's what I've got a diagram of here. So we can see sparking, and usually when we've got something like this, a Van de Graaff generator which is charged, it'll be charged, in fact I think it's charged positively. So compared to the Van de Graaff generator here, which is charged because it's had all its electrons removed, this is relatively speaking negative. And what you'll notice here is a wire, and that wire goes to Earth. That wire going to Earth is basically giving away that this Van de Graaff generator can become discharged. Okay, right, when it becomes discharged, what happens is sparking. So sparking happens when the potential difference, which you should know is measured in volts, is great enough to effectively turn the air between these two objects into a conductor. Now, when the air becomes a conductor, at really high potential difference, the current can leap from one to the other. So the current leaps across the gap, we see a spark, and the object becomes discharged. So we see a spark, object discharges. Now, what you might have seen if you've used the Van de Graaff generator before is we get a spark, and then a few seconds later we'll get another spark, and a few seconds later we'll get another spark, and so on and so on. And that's because this is constantly building up charge. If you were to do this with something like if you were walking up a flight of stairs, and you touched a handrail and you got a tiny little electric shock, then that would be you discharged. You wouldn't get another shock straight afterwards because there isn't the constant movement that you get with the Van de Graaff generator, so it's not constantly building up the charge. Right, so that's it as far as Spec 2. When we move on to Spec 3, there is only really a really small amount of triple only content that we need to make sure that we get into this. And it's all to do with pressure. And it's particularly to do with pressure in gases. So what you can see from this diagram here is that in a balloon, like in any gas, the pressure is always pushing out in the same direction. And the key thing here is that the pressure is pushing out in all directions, because the force is perpendicular to the surface. And that's any surface at all. So if the floor is here, then the pressure that the gas exerts on the floor is perpendicular to that surface. If I am stood on the floor here, and this is me, then the pressure acting on me is perpendicular to me, depending on which way I am facing and which part of my body the force is acting on. Okay. Any surface, the force is always perpendicular to the surface. Now, what you also need to know about pressure is that when we have something called Boyle's law, which is associated with pressure. And Boyle's law is basically that the pressure and the volume of a gas at a given temperature is equal to a constant. And what that means is that if we have a pressure and a volume of a gas and we change the pressure of that gas, then the volume of that gas responds, accordingly. So just to give you an example of what I mean by that, let's say we have a pressure of 1,000 pascals, and the volume of the gas is 1,000 litres. 1,000 times 1,000 is 1 million. If I change the pressure of that gas and I halved the pressure of that gas to 500 pascals, then basically the volume would respond inversely proportional to the pressure. As one increases, or in this case decreases, the other will increase. So if that decreases to 500, then to compensate, the pressure has to increase, because we still need to get a situation where the answer to both of these sums is the same. The pressure times the volume is always equal to the pressure times the volume. And if the pressure decreases, the volume has to increase. And if the pressure was to increase, then the volume would have to decrease, and so on. And it might give you a situation here where you had to calculate the constant and then use that constant to figure out a new volume if the pressure changed, or a new pressure if the volume changed. Okay, Boyle's law is not very complicated maths. It's just remembering that it is a constant. Pressure times volume in the first situation is equal to pressure times volume in the second situation. Now, the other thing I said that we needed to know about is temperature. So there is a relationship between pressure and temperature, and it's a straightforward one. It's basically, as we increase the pressure, we increase the temperature. And the reason for that is because when you increase the pressure, you have to do work. The reason that you do work is because you apply a force to increase the pressure of an object over a distance. And as you should already know, force times distance equals work. So when we do work, we use energy. We use energy in the form, and we measure that, we use energy and we measure that in joules. So doing work increases the pressure, and that increases the temperature, because when we add or do work, we effectively increase the amount of energy that this object has. And the particular type of energy that we increase is the kinetic energy. The trilogy content teaches us that kinetic energy and temperature are proportional to each other. So if I increase the amount of kinetic energy that an object has by doing work on it, then I must therefore increase its temperature. Okay, right, that pretty much covers that one and that spec. The one with the most content that's triple only content is spec 4. And spec 4 is the one that's all to do with atomic structure. It's all to do with alpha, beta, and gamma radiation. But it's really the application of these things that makes it onto the triple only content. The first thing that I want to look at is background radiation. So this is the radiation that we are exposed to all the time. And it comes from a variety of different places. The majority of these places are natural sources of radiation. So, for example, rocks are natural sources of radiation. Even if we use the rocks to make buildings, these are natural sources of radiation. We did not put the radiation into the rocks. Cosmic rays, the majority of these coming from the sun. Food, which usually gets there from the soil or from the rocks. And then we also have radon gas. And radon gas is radon is basically a radioactive noble gas. So because it's noble, it sticks around for a really, really long time because it's really, really unreactive. It's very, very dense, so it accumulates in holes in the ground, particularly very, very dense rocks like granite. And we find high concentrations of granite in places like Cornwall. So Cornwall is associated with lots of radiation, predominantly from radon gas. And radon gas is one of the things you have to have your house tested for when you buy a new house. This section here, artificial sources. Artificial sources, we're kind of conditioned a little bit to believe that artificial sources make up a really high proportion of the amount of radiation that we're exposed to, but they really don't. 18% of the radiation that we're exposed to comes from artificial sources, of which a really, really small amount comes from nuclear power and weapons testing and other sources. So these are really, really tiny, tiny amounts. Yet we're conditioned to believe that they're really, really dangerous. They're also very, very well focused. So you find really high levels of radiation in places like Chernobyl in the Ukraine. You also find really, really high levels of radiation from artificial sources in a place called Fukushima in Japan. Both of those are associated with nuclear disasters. Even in Hiroshima, where there was the first ever nuclear explosion, the levels in Hiroshima are about 2 times the normal level. So even though an explosion happened directly there, it's not that high. It doesn't have that big of an impact. The big one here is medical. Now, medical is also obviously variable. It's dependent on the person. So if you have lots of x-rays, then you will have a higher proportion of this. If you've had to have radiotherapy, then you will have a higher proportion of this. If you've had to have, a gamma camera used on you or anything like that, then the proportion of background radiation that comes from medical will be higher. Now, a lot of the questions that you get based on this will all be to do with data. You'll be getting information a little bit like this, or potentially a little bit like this. And within this, you'll get the unit given to you of the amount of radiation that we get, and we measure that in sieverts. Okay, basically 2 sieverts is enough to kill you instantaneously. Now, what we deal with usually is millisieverts. So 1 millisievert is 1,000th of a sievert, and the average person gets 2 1,000th of a sievert every year. So clearly the chance of you dying from radiation, from background radiation, is pretty small. Now, what you can see here is shows the effect of radiation dose on the human body. So this backs up what I just said there. 1,000 millisieverts, which is radiation sickness, but probably won't cause you death. 10,000 will lead to death. And then 100 is the lowest dose with evidence of causing cancer. And you'll be get questions where you have to interpret the amount of radiation produced by something. So we've got a granite worktop producing 0.003 millisieverts per day, and we have to equate the amount of radiation produced by that to lead to a risk here. Okay, so we would look at this and say 0.003. We would look at 365 days being a year, multiplying those numbers together and looking at where it fell. If we had a granite worktop causing radiation sickness, it's very unlikely that you'd have that granite worktop in your house. If you even had a situation where that granite worktop led to cancer, again, probably unlikely that you'd plumped for a really nice granite worktop at the cost of getting cancer. So very, very often data-based questions linked to background radiation. Then we get onto specific uses of radiation. So this here is a gamma camera. And what this is basically a detector that is designed to detect gamma radiation. And it produces images, and those images will show on that screen there. Now, in order to detect gamma radiation, somebody would have to have gamma radiation or a source of gamma radiation injected into their body. It might not be injected, it might depend on what part of the body they wanted to look at. So if you want to look at your blood or your heart, you'd inject it. If you wanted to look at kidney function, then you'd drink it. If you wanted to look at your digestive system, then you'd eat it. Might get you to breathe it in if they wanted to look at the function of your lungs. All of the things that have in common is that you can look at soft tissues that you can't in an X-ray machine, and you can also look at moving and living images, which you can't in an X-ray machine as well. So we can look at this, and we can look at lung function, or we can look at kidney function, or things like that. Now, gamma radiation is really important here because gamma radiation is the most penetrating type of ionizing radiation, which means if you put it inside you, then it will penetrate through your skin and will be detectable outside the body. So because it is the most penetrating, if we gave you something containing gamma radiation to drink, it would go through your body systems and it would probably accumulate within your kidneys. So what you'd be able to do then is get images of your kidneys and interpret what they looked at. Now, if you're given a question on this, what you're likely to be asked is to talk about the ideal properties of a radioactive source. This is a really quintessential question here. And what you'd be really careful of is what you'd want to look at is making the right choice in terms of the type of radiation. We've already said that gamma is a really good one because it's penetrative properties. But it would definitely not be alpha. Now, alpha is a bit of an issue because alpha is the most ionizing radiation, so it causes the most damage, but also it is the least penetrating. So if you put alpha radiation into someone's body, it would not get out. You may have seen pictures of Alexander Litvinenko, the ex-Russian spy who was killed in the Ritz in 2006 by being given some polonium-210, which was a source of alpha radiation. You might get away with beta because it is penetrating enough to exit the body, but generally speaking, we use gamma. Now, there is another property that you need to consider here, really important property that I haven't yet mentioned, and that's the half-life. Now, you should know that the half-life is basically the time taken for the activity of a radioactive sample to reduce by half. And what we're looking for here is a short half-life. Because if we have a short half-life, then the gamma radiation source that we put into people's bodies doesn't stay radioactive for that long, and therefore it won't cause people that much harm, or it causes people the least harm possible to get the benefit that we want. So that's a gamma camera. The other type of radioactive use of radiation in medicine that we need to be aware of is radiotherapy, and there are two types of radiotherapy. There's a gamma knife, and there's also internal radiotherapy. So gamma knife is effectively external. So we have this machine again, it looks a little bit like a gamma camera, but rather than detecting, this time it's producing the radiation. And what happens is we have lots and lots of radioactive sources, and these radioactive sources fire a beam of gamma radiation through a patient's body, and they are designed to center at a particular point, usually where the tumour is. So if you imagine, if this here is somebody's brain, and here are the two hemispheres of that person's brain, and within that person's brain there is a tumour. If I fire some radiation along this line here, then everything along that line receives a dose of radiation. If I move the position and then fire the gamma knife again, then everything along that line gets some radiation. The key thing here, that the centre of the circle, the point that continually receives a higher dose, is the point where the tumour is and where the beams of gamma radiation are overlapping. So everything gets a small dose apart from the tumour, which gets a high dose. The intention is obviously to kill the tumour and to damage the surrounding tissue as little as possible. Internal radiotherapy works using things that look like this. This is basically a radioactive implant. And the premise is kind of a little bit similar to the hormonal implant that people use for contraception. This releases radiation slowly over time. And what they do with it is they implant these little implants where the tumour is. So they release their radiation directly to the tumour. Because it's very, very close, the penetration of that radiation into surrounding tissues isn't that high. So the range of where the radiation hits is not that high at all. So we can hopefully have a greater effect locally than we might have systemically by using something like this. We don't have that beam of radiation going all the way across and affecting everything because it's very, very local, although it will affect tissue around the outside there. Got another example of a question here which mentions the half-life, a short half-life rather than a long half-life, and that's to do with how long that material will stay radioactive for inside the body. So it's not just, when you get a question like this, it's not just type of radiation used and the properties, but also the half-life. So if you get a table of data which gives you information on the type of radiation that something produces, but also the half-life, then make sure when making your decision, you take both of those into account. Right, last couple. Nuclear fission, nuclear fusion. So nuclear fission, the first thing that happens in nuclear fission is a neutron is absorbed by a large, unstable nucleus. And that is probably something like uranium-235. Might also be plutonium, but uranium's a good one to remember. So when this nucleus absorbs this neutron, it becomes even bigger, even heavier, even more unstable. And when it becomes even more unstable, it splits. And it splits into a number of different things. It splits into 2 or more smaller nuclei. Typical things might include things like krypton. I think xenon might be made sometimes. Don't really need to know that, it's not that important. The key thing is that this big one splits into 2 smaller ones. But this is not a clean split. And what we get produced there is more neutrons. Usually 2 or 3 extra neutrons. At the same time as that happens, we get loads and loads of energy. And what literally happens is some of the matter, some of the mass involved in this neutron and this first nucleus is converted directly into energy. So we have lots and lots and lots of energy produced. The next thing that happens is that these neutrons here go off and basically go and hit another or absorbed by another uranium-235 nucleus. So this neutron here goes and starts this process again. At the same time, this is doing the same thing somewhere else, and this one is as well. We call this a chain reaction. Basically, through a chain reaction, 1 neutron can lead to the production of 3 more neutrons, which can lead to the production of 9 more, and 27, and 81, and so on. So very, very quickly, this number gets bigger and bigger and bigger. Unfortunately, this can be uncontrolled. And if not checked, can lead to so much energy that we get an explosion. So often in a nuclear power station, we use something called control rods to slow this process. And control rods are usually made of boron, because boron is really good at absorbing neutrons. So what you have in a nuclear power station is you have nuclear fuel rods here, and these nuclear fuel rods will be submerged in water or another coolant, and the heat from this reaction will heat the water, and it will go and turn that into steam and turn a turbine, things like that. But between them, we have these control rods, and these control rods can be moved up or down, depending on whether we want the reaction to speed up or slow down. And if they're fully submerged into between the fuel rods, then it will slow it right down and really, really slow down that reaction. If they're taken out, it will speed right up. Just linking back to Chernobyl again, in that disaster that happened, is these were fully removed from the reactor, and what happened then is these got so hot that they actually melted down, and the massive explosion, and the fuel rods melted into something called the elephant's foot, which is now accumulated at the bottom of one of the reactor buildings in Chernobyl, and that's why it's still so hazardous to go there today. Final thing is fusion. So in fusion, it's almost like the opposite. Where fission was splitting, fusion is the joining of nuclei. So in this situation, these are small nuclei. Okay? When we're joining things together, it's easy to join small things together. When we're splitting things, it's easier to split the large things. And we take our two small nuclei. This is deuterium and tritium. These are both versions of hydrogen. That's hydrogen 2 and hydrogen 3, different isotopes. And these are pushed really, really close together under a situation where we need a ridiculously high pressure and ridiculously high temperature. When that happens, you overcome the repulsive force of these nuclei, because this is positive and this is positive. They both want to push each other apart. When we push them really, really close together and increase the temperature, we can actually get them to fuse. And if they fuse together, they make helium, and then there's some neutrons produced as well. That makes significantly more energy than nuclear fission. Also, the products that we make is only helium, so this is not radioactive. Also, one of the other major advantages of fusion is that there's no chain reaction. So if we want to stop this process, all we need to do is reduce the pressure and the temperature, and the reaction will stop. That's a major advantage of nuclear fusion over nuclear fission. The biggest issue is the high temperature and the high pressure. And at the moment, scientists are investigating something called cold fusion, where we're trying to drop the pressure, drop the temperature, because at the moment we aren't making enough energy from the process to make it worthwhile doing. And if we actually get to that point, then what that will mean is pretty much unlimited clean energy for a long time, because the hydrogen that we use in the process to start with, this comes directly from water, so not very complicated at all. Okay. That's pretty much all of the triple content. Like I say, if you do have any comments you want to put on the video, then just add them onto the bottom. We'll try and respond to as many as we can, but obviously we won't be able to do that live. Sorry that we couldn't go live tonight. Hopefully you'll realise we've tried to do something useful for you anyway, and best of luck tomorrow.